So I will talk about subglacial geology, but more from the perspective of airborne geophysics, mainly gravity and magnetic data. And obviously, I'm working in Antarctica. So the problem with Antarctica really is that most of the subglacial geology is hidden beneath a thick ice sheet. And we only have limited information about the geology directly. Direct information comes from areas where we have high mountain ranges or close to the coast. And basically, over 99% of the geology is hidden. So we need different ways to try to infer the geology. And on that figure, we see on red locations of rock outcrops. So there we are certain what the geology is, but everything more interior in Antarctica, it's hidden away. And there's no reason to believe that the geology in Antarctica is less complex than any other place on the planet. So really, why we're interested in the geology of Antarctica is to better understand the tectonic evolution of this remote continent, but also subglacial geology influenced strongly the geothermal heat flow, the thermal regime of the crust, and therefore plays a quite significant role in the ice sheet stability. And if we think of current challenges, humans, or we on a global scale face the ice sheets in Antarctica are quite important. So it's quite important to understand the geology beneath. And on that talk, I will focus more on the crustal properties, but the heat flow or the thermal regime will always come up as like a background motivation why we care about those things. So we cannot go to Antarctica and just look at the rocks and understand the geology. What can we do to infer subglacial geology? We can use different geophysical methods like airborne gravity and magnetic data, but also radar measurements. So we can penetrate the ice and then get precise information about the top of the bedrock beneath. There's also seismology and seismic experiments we can use to understand the crust or the lithosphere in Antarctica, but that will not be a part of this talk. So if we try to understand how we measure crustal structures in Antarctica, we can use airborne geophysics. So the British Antarctic Survey is quite good at flying airborne surveys. So we see our little aircraft flying above a cross section. So basically, we have our crustal properties, and every rock provenance has a different density and stability, which influence the gravity field and the magnetic field. So if we fly over with our aircraft, we're picking up all the different sources as we're measuring the gravity and the magnetic field. And then from that data, we can start trying to model the crust and put the different sources and give them different density and stability to understand the crust, or we can use inverse problems, which we will talk later in the talk about. But basically what we can see is like we in that simple sketch that if we have sediment basin, that will have lesser density than the crust. If you have intrusions, that will usually have higher stability than the surrounding things. So we can start trying to unravel what the crust and the geology looks like. So in Antarctica, there's a lot of effort, what was done to measure the gravity and the magnetic field with airplanes, and that's a compilation of the gravity and the magnetic field for Antarctica. So we can see in the gravity that we don't have a full coverage of the continent, but we have like different flight stripes. So you can see really where the airplane is flying, where we have information, where not. But international collaboration really and the open source or access to the data really allows nowadays to do regional studies in Antarctica, which wasn't possible a few 10, 20 years before. So if we have gravity and magnetic field data or measurements, what we can directly derive from maps like that can try to trace mountain ranges or tectonic features in the magnetics where the minerals align due to tectonic processes differently. But really, if we look at gravity and magnetic data just on a map view, we have pretty colorful pictures. We can draw and trace different lines there, but really getting to understand the crust is if we start using this data to really model in a three-dimensional space the crust. Yeah, and that's what I have done in my PhD the last 3.5 years. One more thing why we should care is geothermal heat flow, really. And just to give a quick overview on that, usually geothermal heat flow describes the heat transport from the interior of the Earth to the surface. And we don't really have any direct information on Antarctica. We have less than 10 direct geothermal heat flow measurements. So then we need to start thinking again how we can infer that, and geophysics play a major role in that. And it's really important to understand geothermal heat flow because that influences the ice sheet. Because a higher geothermal heat flow will lubricate the crust or where the ice is flowing, and that can enhance the ice flow, which is bad then for sea level rise. And also it's quite interesting to understand the whole tectonothermal evolution of Antarctica. But yeah, it's just a parameter we don't really know, but ice sheet modeler really need to put it in their models because it's an important boundary condition to the solid Earth. And there's a way around, and if we don't have direct measurements, so there's a lot of different geothermal heat flow estimates from geophysical data. So we can use seismic studies from magnetics. It's done often with estimating the degree depth and then forward calculating the heat flow, but also recently machine learning and multi-data analysis processes. All these heat flow models have one thing in common, that they see West Antarctica, which is this bit over here, that it's much hotter than West Antarctica, which is an old craton and believed to be quite cold. But if we zoom in into certain regions, for example, the Wilkes Subglacial Basin and the Transantarctic Mountains, we quickly see that those models don't agree that well. They are quite different, the patterns are different, the amplitude is different. And I don't really want to mark or to judge which model is the best, mainly because I have one model in the mix as well. The issue with all these models is really that they don't incorporate the crust or any subglacial geology information. So basically, they treat the crust as a homogeneous block with global average parameters in terms of thermal conductivity and heat production, and neglect any heterogeneousness in the crust. And there's no reason we should believe that the geology in Antarctica is simple, basically. And that's really the main motivation why we should start to try to unravel the crustal properties in Antarctica, so we can incorporate those into the heat flow models on the next generation of heat flow models, and then we maybe can predict better sea level rise in the last instant if we understand better what the ice sheet is doing. Yes, so that's the background motivation really to all the studies I'm doing. And this last slide of the introduction really illustrates that quite well, that heat flow has a large contribution from the mantle and asthenosphere, but if we just zoom in a little bit up here in the upper crust, we see something called HPE here, which is heat-producing elements, and they are usually concentrated in the upper crust. Minerals like uranium, thorium, potassium, which produce a lot of heat, and they can influence the heat flow locally quite significantly. And yeah, up to 40% of surface heat flow can be contributed to radiogenic heat production. So it's a really important quantity. And if we neglect that bit in heat flow estimations, we miss quite a large portion of importance. Yeah, and just to make the point, like a difference in heat flow of 20 milliwatt per square meter can change how much the yearly basal melt rate is from around 6 to over 18 cubic kilometer a year. So it's quite significant in terms of the ice sheet and melting from below. So the reason why it's not in the current geothermal heat flow models is because we just don't know the crust that well. So if we don't know it, we cannot really incorporate it in our models. So that brings us to my research, where I tried to figure out what the main crustal blocks and provinces in the Wilkes Subglacial Basin and Antarctic mountains are. And if we think back to the first sketch of the crust, one way of model using gravity magnetic data would be a forward model where you put different blocks and structures in, give them a density and susceptibility value, and then you try to fit a model that explains the observed gravity magnetic field quite well. But that's quite biased to the person who's doing it. The other way around would be to use inversion. So we use an algorithm that puts susceptibility density values automatically, so that takes out a bit the bias in the modeling process. And how we do it is we discretize our study area in a three-dimensional block, and we have different cells there, and then iterative, we change the susceptibility density value jointly, and then with increasing iterations, we will reach a model, or we will obtain a model that explains the observed values quite sufficiently. Without going too much into the math behind it, we don't really need that to understand that here, but one very important variable we need to talk about is the objection function. So basically, we discretize our crust into many little cells, and then iterative, we try to solve for the best model. The criteria we use is variation of information here. So the objection function we're trying to minimize is VI here, and it has 5 terms. So it has the misfit to the forward calculated gravity field and the observed field, the same for the magnetics. Then we have 2 regulations parameter, which basically describes how smooth our model is. And then we have the last bit, which is the variation of information, and that's a quantity which is closely related to mutual information, basically enforces a coupling between gravity and magnetics. So the idea behind it is that if we have a rock provinces in the crust, we assume that that geometry causes the gravity and the magnetic field. So we force the inversion to find similar structures in both the this density and the susceptibility modeling. So that's our input data, airborne magnetics and airborne gravity data. That's Bouguer anomalies, so corrected for ice and topography, and we also remove the sources below the moho, so everything from the mantle is already removed. So it's a more residual gravity field. And if you look at the map, we see here a very prominent high linear feature, which is close to the area where the transition zone to the craton part. And in the magnetics, we have two very prominent high magnetic features here in the interior, and then a few along the granigram and offshore. So if we run the inversion for over 100 iterations, we get an inverted field that looks like this, which resembles quite nicely already the observed field. And the residual, so basically subtracting the inverted from the observed field, we get the residual field, which looks like that. And the errors are really been within plus and minus 10 milligal, and the misfit in the magnetics or in the susceptibilities in the magnetic field is quite good as well. It increases quite sharply towards the edge of the study area, and we have some edge effects around data gaps. But overall, it's also plus minus 10 nanotesla, and then in the region where the general field goes from plus minus 300 to minus 300 nanotesla, we have transitions quite sharply to over 2000 nanotesla. So in that region, we don't fit the field very well, just because the inversion really prefers smooth transitions rather than sharp ones. So, and the field changes here quite rapidly. Talking about the cells and how we set up the model, that's an illustration of our cells. So basically, we have topography information telling us where the top of the model should be. So cells above are within the ice domain, and we said that we don't allow those cells to vary in the inversion, and only the yellow cells are allowed to vary, to change iteratively within the model. And we have two different boundary conditions actually for the two different fields. So for the gravity field, we removed everything below the crust mantle boundary. So basically, the moho depth is the boundary condition for the density inversion. And for the magnetic inversion, we use the Curie depth estimation, which is a boundary within the lower crust, and everything below that should be non-magnetic. Here's a map view of those boundary conditions. So here one on the top is the moho depth, and below is the Curie depth, the Curie point depth estimation. And just to explain what Curie depths are, basically from the magnetics, we can, if we have a magnetic field, or airborne survey, we cut out different windows, and within that window we do a Fourier transformation, and basically go from the space domain into the frequency domain, and then from that we can, from the different parts of the magnetic spectrum, we put straight lines through the the long wavelength part and through the medium part, and those different linear sections in the magnetic spectrum correlates to different depth within the crust. So basically, that part here gives us the top of the bottom of the magnetic layer, the centroid depth, and the the middle part gives us the top of the magnetic layer, and then by just applying the simple equation down here, we get the bottom of the magnetic layer. And that's important because magnetic minerals lose their magnetization with temperature. So that's the Curie temperature at 580 degrees Celsius. So by finding the lowest or the deepest at the bottom of the magnetic layer, we assume we find the 580 degree Curie isotopes. Yeah. So yeah, basically we take the window, we move it in a moving window approach and redo the analysis for a lot of different windows, and then we get a spatial information about the Curie depth, which looks in that area like that. So red is shallow Curie depth, which means the mantle would be higher. Therefore, we choose red colors because of technically is already in the warmer region, and blue colors indicate deeper Curie depth, which means it's a colder thermal regime anyways, if we ignore any heat production in the crust. And from that, we use that estimation as in our inversion as the bottom of the magnetic layer. So basically, if we go back, we invert jointly until the Curie depth point, and from the Curie depth point down to the MOHO, we do only gravity inversion. Yeah. So here we see now a depth slide at 12 kilometers through our model, which resembles different parts quite nicely, but really it is a joint inversion, as it means that we find geometries and different density stability values that explains the observed field, but from the horizontal slides, we don't really see that well what the inversion is doing. So if we cut through and do a cross section, that illustrates it much better. So we find identical geometries or structures within the crust. Here the dotted circles in red and in blue, and they're quite nice figures. So we couple the gravity magnetic field or the density stability inversion to find identical structures, but there's no linear relationship. So basically, we have a structure here, but in the density, it's slightly negative values, while in the stability, it's positive. And then if you look at the next pattern, it's both negative. So it doesn't really matter. Like a high stability anomaly doesn't need a high gravity anomaly. So the values within the structures can change, but the structures are consistent. And it's quite nice illustration here as well, that we have the same lobs, but different amplitudes in that area. And we see here polygons drawn. So one thing we're really interested in is, if we look at the different distribution of density and stabilities, we would like to contribute those anomalies to rock types, basically. And to do so, because the gravity and magnetic field isn't in the Wilkes Subglacial Basin, it isn't like one correlation. We needed to find the structures we're interested in. So for example, the IB1 here. So we drew a polygon around that. We took all the values in that area and then thresholded it against high positive stability values, so we get rid of the errors around. And then we get for that structure as density and stability distribution. And if we look within the same standard deviation of the extracted structure, we can then filter the whole model and try to find identical regions with identical petrophysical properties. So we are we're hunting for IB1, another structure which we see in the gravity inversion is the CM, the linear high density feature along here, which is basically the suture zone to the craton. So we extracted both of those structures, and then we can plot them on a density susceptibility relationship graph, basically. So in gray is the whole model, like the distribution of density and susceptibility is in gray, and then the different colors is then the things we thresholded, pulled out the structure, and then we calculated the mean of the extracted structures, and then the error bars. It's not really an error bar, but it describes the standard deviation in that structure. And what we can already see quite nicely is that those two different structures separate quite nicely on the relationship plot. And if we then filter the model and search for the same areas, we get basically areas with identical or with the same petrophysical relationship within the model. And what we can see here is IB1, which we believe is an intrusive body, has the identical signature to the next related magnetic anomaly. So we believe actually that probably IB1 and IB2 has the same origin, which wasn't really, well, IB1 you could clearly see in the magnetic data there's something. IB2 was much more diffused, but the inversion tells us it has basically the same relationship. So we're thinking of that both have the same origin and probably were emplaced at the same time. Very important for later, so keep that in mind, is Cook E2, which is a subglacial lake, and we will talk about the fellow later. But just keep in mind that it sits directly in the one body we have identified. That's important, and then we will come back later to that. Another thing, so basically based on the density susceptibility relationship, because it is quite very important is that's relative densities and susceptibilities anyways. So we would add the crustal, mean crustal density to it to convert that to absolute densities. So that area here, IB1, is very close to the crustal background. And we believe based on the relationship that because it's quite low susceptibility and around 2.6 in crustal in density, we believe that is in granite. So we have a big, massive granite intrusion. And knowing the Wilkes Subglacial Basin and the Transantarctic Mountains, what is plotted here in red is actually the granite harbor intrusive, which is a granite intrusion that happened during the Ross origin, so 500 million years ago. And because that's the rock outcrops for the Grand Harbor intrusive are in the Transantarctic Mountains, so we have direct information with that. And very surprisingly, when we looked at our inversion model, we believed, or we suspected that the green bits would overlay with the red ones, but they don't. So that indicates that those intrusive events are separate in space and time, which is quite interesting. So from that, ignoring the crater margin now for the moment, but basically the geology in the Wilkes Subglacial Basin goes from younger to older, and the oldest thing we found is around 500 million years, so the Grand Harbors. But in sediment cores or in erratics from glaciers, we have found circles that indicate much older ages, around Pan-African ages, so 680 million years ago. And nobody knows where the source of that body is. Very speculative on geophysical modeling, but if those bodies here are actually an intrusive event that happened earlier, that could be an explanation where the source for the circles in the sediments are coming from. So based on fully gravity magnetic modeling now, we started to sketch up a geological map or evolution of the Transantarctic mountains and subglacial basin. And basically what we see is we have the craton on the right side, passive margin developing around 660 million years ago. And we have underplating, which gives us the high densities and probably the high magnetic amplitude, because that's remnant magnetization then, which would account for the high amplitudes we see towards the craton. And then around 650 million years ago, we would have a subduction zone developing, and then that causes the emplacement of the massive batholite we see in our model. In the cross section, we kind of see that they are connected. If we just look at the sustainability density relationship based on the standard deviation, we would have a separation between, so maybe it's a continuous body, maybe not. And then something around the Ross origins 500 million years ago happened that either the subduction zone retreated or stopped and a new one developed, and then we have the emplacement of the Grand Harbor. So that's our idea, and then we come to a present day scenario in the Wilkes Subglacial Basin. Very speculative, but spectacular geological interpretations in Antarctica have a long history, because we just cannot go there and measure, but based on gravity and magnetic airborne data and the joint inversion, it's something we should suggesting at the moment. The paper is now in the second review phase because not everybody agrees with that sketch. But that's what we can get out of the inversion a bit. Maybe I didn't mention that, but yeah, it's a quite nice fit between the observed and inverted fields. Also important to mention that gravity magnetics is non-unique, so there's an infinity of models where you could change the structures to gain a similar good fitting model. The non-uniqueness is a bit reduced by using both fields simultaneously, but still it's always a problem in gravity magnetic modeling. So what would that imply for the heat flow if that's a batholith, if we accept the interpretation, and we cannot really go there and look at the batholite or the intrusion body, but there are two very prominent batholites and large-scale intrusions visible in Antarctica, where we can go and measure, and we see that we have really high heat flow if it's a granite intrusion, and we can compare that to the granite batholite in Cornwall as well, which is along the red line around 200 kilometer long, and that's roughly the same order of magnitude the inversion model predicts as well. So that could imply that, in fact, yeah, we have one of the batholites. It's not unheard of to have that large-scale batholites anywhere else, and even in Antarctica. And if we find them, they are usually a target for geothermal geothermal power plants because of the high heat flow. Talking about the Cook E2 subglacial lake, so that's a really large subglacial lake that was identified by airborne radar data 15 years ago. And it's a lake that is up to multiple hundred meters thick, so deep. So it's a really prominent lake in the area. And what I really find fascinating that if you overlay that lake on all the current geothermal heat flow maps, we see that the lake is most of the time located in the low of the heat flow models, which is quite interesting, but because usually you would need high heat flow to support a big lake like that. So that really indicates that let's put it that way, that those models don't explain why the lake is there. But if we think that actually there is the big batholite intrusion, that would increase the heat flow in that area and would explain why the lake is there. And that really gives an understanding why most of the models, well, they don't have local geology in there, so they will miss local variations in the heat flow. So the current heat flow models cannot really resolve the presence of lakes, more or less, if you ignore all of geology, more or less, or if you ignore anything that happens in the crust. Unfortunately, there are much more lakes, smaller ones, and if you display all of them, yeah, there's no correlation really with the current heat flow models. Maybe my model does a quite good job in some areas, but I don't want to overinterpret that, because really in my model, and anything that happened in the crust is removed as well. So yeah, so I've talked quite a bit now about gravity magnetic data, what we can do, what we can get out of it in terms of 3D structures. We haven't really looked into geological information and maybe trying to use actual geology to validate inversion models. And if you remember the first slide where we saw that in high mountain areas, we actually have geology. We can go back to the Transantarctic Mountains, and we have quite a few information about rocks there. So that's a geological map, and that's based on geological surveying. So all the different colors are basically rock outcrops, which were studied. And one leading group doing northern Victoria land, so where the Transantarctic Mountains is the German BGR. They have a history of going into that region for over 40 years, and they collected a lot of rocks. So I went there to do susceptibility and density measurements on different rock types. And that's, yeah, I get asked quite a lot during my PhD, how was Antarctica? And if I went there, never went to Antarctica, never did fieldwork. My fieldwork was going to Germany and look at rocks, which is equally exciting, I think. So the BGR has two different rock archives or polar rock archives. One is in Berlin-Spandau and one is in Hanover. And they basically have two of these massive corridors with a lot of rock samples, multiple thousands. And I was handed a key and I stayed there for a week just doing susceptibility and density measurements on rocks from the Transantarctic Mountain area. So basically, susceptibility we measured with a Kappa hand sensor, quite quick, and then density we inferred by bringing the rock sample into suspension water and then based on the displacement of water, you can figure out the density. And I managed to measure 320 rock samples within my study area, which is quite an achievement, I guess. The location of the rocks are, of course, very biased to the expedition the Germans are doing. So the Gunwick's expeditions have different focuses and know only where they went. We have basically rock samples. But I think I covered at least quite nicely the whole area. And the advantage of those rock measurements is that we have rock type and also the formation. So from that, we can start trying to verify our inversion models. So in purple here again is the Granite Harbor intrusive. So from GeoMap, we know the location where the Granite Harbor intrusive rocks are. We just sample the inversion model for the locations where we know Granite Harbor rocks are. We pull out those values or the density sustainability values for the Granite Harbor polygons. And then we look at what I've measured in Germany for the Granite Harbor rocks formation. And what we can see here is in red is the inversion results, in blue is what I've measured. And if you just look at sustainability values, most are around the 0 mark, but we have a few outliers. And the inversion also puts most of the values towards none or just a little bit magnetized rocks. But the inversion also gives us outliers, and the range of the outliers is a quite good fit, I think, with what we have measured. The gravity is not really that well resolved. So on the y-axis, we have the densities, and the inversion, most of it is within what we have measured, but we have a lot of outliers up here, which the inversion cannot really resolve. From that, we would say, maybe not that great, but we can then also break down the Granite Harbor intrusive formation in the different rock types. So if we do that, we see that granites and diorites are quite nicely matched by the inversion. And that's also where we have the most rock measurements. So we have almost 40 granite measurements, diorites 9, and then the outliers are above. We have much less samples of them, but also if you start thinking about what those rocks are, a hornblendite, this is quite rare rock anyways, which is really dense, with densities typically found in the mantle. So they are not really representative for the main crustal rocks you would expect. And then if you start thinking about the resolution of the inversion, so the inversion cells are 7.5 kilometers by 7.5 kilometers. That a cell represents such rare rocks that we would need a GAPRO, for example, 7.5 times 7.5 kilometers cell to fill that, and you don't have displacement of that large GAPROs. They are much rarer. And so geology is really on a smaller scale than geophysics can resolve. And that demonstrates quite nicely that we can resolve the main crustal rock types and features, but we cannot go in like really fine scale, geological scale mapping and resolve like little GAPRO or hornblendite regions, which you would find if you go and actually do geological mapping, just because of the cell size. So basically, our inversion cell size is a average of everything you find in that 7.5 times 7.5 kilometer window. So another quite unexpected turn in my PhD was then when I went there and do the measurements. The yellow area up here highlighted is the Mesa range, and it turned out that BGR actually flew a magnetic survey with a helicopter with 500-meter line spacing there. Data is not really publicly available, but I got my hands on it. It's not clear, so they have sent it to AdMap, and it should be in AdMap, but it's not clear if it's in AdMap. So there's a bit of gray area, but the raw data is definitely not publicly available, but they're planning on publishing that. Maybe a step back. The reason why we inverted with 7.5 times 7.5 kilometer cell size is because the flight lines of the aircraft is 10 kilometers. So every 10 kilometer, you get one line of magnetic and gravity measurements. And there's no real reason to go into like a kilometer size resolution if the input data doesn't provide that. With a high magnetic survey, like 500-meter resolution, we actually can rerun inversions with a much higher resolution or cell size. So we're going now in the Mesa range region. And that inversion, we only can do magnetic inversions because they didn't fly gravity measurements. And if you look into the current airborne gravity data set, it's only 3 flight lines passing through that area, so that's you only get the really long wavelengths, and if you jointly invert those, they don't give a really good result. So we got rid of the density, but inverted for magnetic only, seen up here, and now the cell size is 250 meters by 250 meters. And looking at cross sections, we can pick up just from the intensity of the measurements different rock types already. So we have Kirkpatrick basalts, which is a flat basalt, really high magnetics. We can identify that quite well compared to the FD, which is Farrar dolerites. They are much lower in the amplitude. And we can quite nicely constrain that those bodies are really close to the topography of the area, which is quite nice because we know from geological mapping that that actually is true. So Kirkpatrick basalts cannot reach depths or thickness over 900 meters, and inversion indicates it's roughly a kilometer in size. A bit annoyingly is that the inversion algorithm spreads into deeper, the signal is bleeding into deeper areas, but where the real main area sources are, it's quite close to the topography. And then we can basically do the same exercise. So in green down here, we have geological information of the Kirkpatrick basalt. Blue polygons are the Farrar rocks, and then purple is the Grand Harbor intrusive. Because we know from GeoMap the locations where the rocks are, we can then sample again our inversion for that. Up here, we see the histogram of the inverted values in sustainability. And basically, we then filter again against the different units from GeoMap, and we get red is what the inversion tells us Kirkpatrick basalt is, blue is the Farrar dolerites, and gray colors are the Grand Harbor intrusives. And the lines basically describe, so everything below the line adds up to 1. So we see that Kirkpatrick basalt is a bit more spread out. But if we then start to filter again against locations, we see that this is quite, so we thresholded the susceptibility values for those two ranges. So for Kirkpatrick basalt range, around 0.02 to higher values. If we plot that, the location, we see that it's a 1-to-1 relationship with the Kirkpatrick basalts, and for the Farrar dolerites, quite nice fit as well. So from here we can start then arguing that areas where we don't have geological information, we are pretty confident that where we put the F, that there's, if you would go there, you will find Farrar rocks. So that's, geophysics could help identify areas of rock types, and then geologists are really keen and go and drill there.
How thick's the ice? How thick's the ice?
Around 2 kilometers. So yeah, they will not do that. Yeah. But just to make a point here, so figure D is what we have measured on the rock samples, and we see that you can distinguish based on the susceptibility quite nicely the Grand Harbor to Farrar and the Kirkpatrick basalts. The distinction between Kirkpatrick and Farrar in the measurements isn't that big. So the error bars again is the standard deviation. So there's a strong overlap, but in density, that's quite a good way to distinguish both rock types. And we use this plot to argue that it is really important to also do high resolution gravity airborne measurements. So usually you have 10-kilometer line spacing airborne measurements. If you do it with a plane, you can take a helicopter or drones nowadays to do higher resolution magnetic data. It would be really helpful if you also put a gravity sensor on it, because then you could actually start with quite high confidence, start to distinguish between the different rock types. Something I would like to highlight here as well is the yellow dotted line along here. That's a sharp boundary between Farrar to the Grand Harbor, and it's quite nice how we could separate those rock types already, and with the adequate gravity measurements, we could actually do more, I think, and get more information about the crust. That's the last slide comparing the petrophysical measurements in Germany to the inversion models, and I think it's quite convincing that. So we split it for the different rock types, and we have for the Kirkpatrick basalt quite good fit what we measured and what we're inverting for. Even more convincing for the Farrar dolerites, I guess. The big peak, I guess, is a bit shifted, but we can live with that. The range is always quite nicely represented. And the only thing I'm a bit annoyed is the second peak in the inverted Grand Harbor. So if that would be not there, then I think that would be very convincing, but it's what we basically can do with gravity magnetic data. So I'm not sure how far we are in time. Maybe I just skip the conclusions a bit. Just say, yeah, we can learn a lot from airborne gravity magnetic data about the subsurface in Antarctica. It's really important to understand the subsurface to find intrusives or intrusive rocks that potentially have a high potential to elevate the geothermal heat flow. And it has a really strong implication for the cryosphere if you have a local concentration of high heat producing elements, basically. And it's not ideal. It's everything is quite uncertain, and everything has uncertainties. And if you start working in Antarctica, you realize quite early on that the biggest enemy you're battling is data coverage. So if it's geothermal heat flow, direct measurements, rock samples, or even just having magnetic and gravity surveys, there's always data gaps, and everything is highly spectacular, but ignoring the crust on a principle also introduces quite large uncertainties, and we should bring together the different communities to really try to get a better understanding of the crust. Then we can understand better the thermal regime there, and that would help ice sheet models quite significant, and therefore we could reduce our uncertainties on sea level rise. A last point on the conclusion, I nicked that from Jörg Ebbing, but he's not here, so I use it. Geothermal heat flow isn't revealed or unveiled, as some of the publications want you to believe. There's a lot of work to be done in the future, and really incorporating crustal properties is quite important. And I think also it's important to move away from continent-wide studies in geothermal heat flow and also crustal properties, and really start focusing on local areas and try to get them right, and then get the implications for the cryosphere right. Yeah, with that, thank you for your attention. I leave my co-authors here to give a bit of contribution. I haven't done all the work on my own. I had quite a nice network of people helping me. Yeah. Yep.
Thanks for the talk. I know much more about Antarctica than working. You showed a lot of, you had your distribution of granites, and they're all quite centered in what was measured and what's inverted. Except there was like a street of granites, some with susceptibility against density, that kind of went off to like the bottom right of the graph.
Here or
Further away before you, that one, your figure D. Those two granites line up on susceptibility going off a bit further. Have you looked at where the geographical distribution is of the granites that don't fit in the inverted granite susceptibility density?
So you mean location-wise?
Yeah.
No, I don't think so. You mean that and
Yeah.
here? Yeah.
Like the two bottom ones and the three rightmost blue points.
Those?
Yeah, those. Yeah, that group.
Oh yeah, those three come from around here, close to the outpost. Those I don't know, but they are also 2,400 in density. It's probably might be a granite, but we had the issue with weathering as well. So some of them, they were really porous, so I had a lot of air in it. So yeah, I would just argue that that's probably just an outlier. Anyways, I've marked them in the measurements as strongly weathered if I realized they were strongly weathered, but yeah, it would be good to check if that's actually the case. But I'm pretty confident that that's what's happening here.
Sorry, that's cool. When you did the density measurements, did you leave them in water to soak? So you didn't measure the density of air as well? Did you just drop them?
No, we put them in water and then like dispense them, that they're floating, and then basically measure the force you're measuring with the scale then is the displaced water, more or less. And no, we didn't let it, like we didn't let them soak for like a day or so. We just put it in. That's it.
That would take a long time.
Yes.
Towards the end, you talked about adequate gravity measurements.
Sorry?
So you're saying that if you had adequate gravity measurements.
Yes.
So I mean, by adequate, I mean, you presume if they were good enough.
No, yeah, no, yeah.
What do you need?
Oh, sorry, yeah, no. Talking about the flight lines and like the resolution of the survey. So for the last study, the helicopter flew in line spacing of 500 meters. So it's a really, for Antarctica, a really high resolution magnetic survey. They didn't put a parameter on it because apparently it's quite tricky with a helicopter. But we looked at airborne gravity measurements and we only had 3 flight lines passing that study area. So basically it is 90 by 90 kilometer cube, and we only had 3 flight lines of gravity.
So what would you need? Would you need kilometer spacing or?
Yeah, just comparable to the magnetics, I guess, because really we tried to do a joint inversion, but then what happened is that the long wavelengths field from the gravity, because we only have 3 flight lines, you would grid that up. You have like a really long wavelength gravity field and a really short wavelength magnetic field. Because we searched or we forced inversion to have the same geometries.
You're not about to invert.
Yeah, it's basically.
But could you, with the assumptions of the connection with the gravity lag, can you not forward model the gravity on the lines you have from the magnetics, even kind of a pseudo-magnetics approach, and just see what the implications would be using the kind of high lines tests?
We didn't consider that, yes.
We had, they are data. I liked it. You don't want to throw it away, but it seems that you could at least use it as a test.
Yes, the other issue with the gravity data really is it isn't really 3 flight lines. It's corner flights for a different survey, and apparently in AMGG they removed most of it, so it's more like there. It's really space information, and yeah, we only tried to put it to invert both fields, and then you would get quite surprisingly better RMS fit, and the residual map looked much better. But if you looked at the cross section, you clearly see artifacts coming from the long wavelengths field, and the gravity field suddenly had short wavelengths that cannot be there, and that came completely from the magnetic. Yeah.
Even if you really cranked up the ducting power, now you said that really high.
So the distribution is too uneven.
It's
You try to apply it as a widget to it.
Yeah.
yeah.
I just think I saw. Sorry, other couple of questions. You showed the spectrum, which looked really nice. Could you do back?
Oh yeah.
I like spectrum. Okay, so I was trying to read the scales on these things. So is the axis on the bottom in this kilometer? So 0.2 is a 5 kilometer wavelength.
Yes, I think so. So it's
so at the top, it's maybe what 40 kilometers maybe, or 20 kilometers at the So when you've got a 4 kilometer or 5 kilometer wavelength, what's your depth of source? What's the gradient telling you depth of source is? You don't particularly.
It's a while ago I did that. Yes, we got overall tree depth estimations ranging from like around 20 kilometers, roughly.
I'm just because the
Between 18 and
the breaks in slope in the horizontal wavelengths are therefore the same order of magnitude as the depth you're going down. Yeah. So maybe that's okay. Just one let's spectroscopy with the global ones. So it's a different kind of problem. But I was. Is there a limit to the resolution you can go to? You know what depths you would see in that kind of spectrum? I don't know. I suppose you'd have to do some forward modeling and have a go.
Yes. Yeah, the maximum depth we got were around 30 kilometer. And if you compare that to the typical Marcos model, I think mine were significant shallower.
No, I'm just impressed because those spectra are really the things of beauty. There's such a separation.
Yeah, it's quite good. What we did
Not quite good. It's really good.
a bit annoying is that we don't really have, for most of them, the spectral peak was missing, so that indicates that you're missing some parts of the spectrum of the data, like the really long wavelength part. But yeah, I mean that was the first study I did for my PhD, and that's published.
That's the 2023.
Yeah, it's GL Solid Earth, and quite interesting here is that there's career depth estimations have been done in Antarctica, Martos, but also others before. And the issue is they used airborne data and used satellite data as well. And in my approach, I rejected all the satellite data and only used airborne data. The big problem is the window size you're choosing. So basically, if you have a 300 by 300 kilometer window, that's a high pass filter. So basically, you cannot have any wavelengths larger than 300 kilometer. The irritating thing I found when I looked at the Martos paper is that, or the recent paper in Western Antarctica, the satellite data they use is below the window threshold. So for the Western Arctic study, they used 200 by 200 kilometer window, and where they didn't have airborne data, they used satellite data, but the satellite data starts at 300 kilometers. So what is happening between 300 to 200 kilometers, which is, you introduce data which cannot be resolved or doesn't have physical meaning, but it will do something to your spectra, I guess. So in that study, we really tried to not use satellite data. But then you have the issue if you do a Fourier transformation that like the window you're taking out, you cannot have data gaps in that. So what I did is I interpolated the existing data, airborne data, and then did a second check afterwards and say, if my window doesn't have 80% of real airborne data, I checked out the window. And that's why I only get a map like that where we have sufficient airborne data and where the line spacing of the airborne data is too large or airborne data is just missing. I don't get any information. So with that approach, I couldn't do a continent-wide career depth map, but I think it's a more honest approach. And yeah, comes down to we need more airborne data and on a higher resolution. Yeah.
So just a quick question. When you showed me earlier the models of magnetic and the gravity data and how well the data was synced.
This one?
No, it was lines of data. There were some lines, but earlier. I mean, beautiful. It starts to make me worry about overinterpretation fitting quite that well.
Yes.
Am I being a Grinch, or is there something that's
there's something in there, I guess. It's
certainly clearly, as you said, underneath, so there are many other bodies you could use. You have to mess around and try other four models just to have a look, or there's a machine learning, I guess.
Yeah, it's something we address in the paper, like the limitations and yeah, the overfitting of data. So the RMS misfit between airborne and like density and sustainability, or in that turn, gravity magnetic, is below 2 nanotesla and 2 milligauss, which is, if you think about airborne magnetics, really something. Because usually you would have 15 nanotesla error anyways in airborne data.
Magnetic environment. That's certainly something. It's better when you get in the magnetic observatory.
But
Is
so the MS looks really overfitted, but the maximum and minimum misfit is around, it's much larger, and then the standard deviation of the error is 10 milligauss and 12 nanotesla, which is more reasonable for the data set. And that's also one reason why we choose quite large cell size for the inversion, is because we don't have better flight light coverage. And then, yeah, I'm pretty sure as
I know a version to really fit the hell out of the data. But as you show, as you said, you've got to be completely honest with yourself when you do that and not push it too far afterwards.
yeah, sure. And that
It is a possible model. It's a model that could exist.
you can keep running more iterations to get a bit more out, but do you really learn anything significant from that then? Yeah, but bridging geology and geophysical resolutions is quite, I think, because I'm pretty convinced that review too is a geologist, and we don't. The discussion is quite on cell size and what is possible to infer. Maybe just to say something to the inversion here, which I forgot. I think it's quite nicely. So you see that for the sustainability, we cut at the Curie depth point, and it's labeled the wrong way. Oh my God, shit. So red is actually the Curie depth point, and blue is the MOHO. But yeah, we cut at the Curie depth point. So all the sustainability inversion is from top of the crust to the Curie depth point, and that's jointly inverted. So all the structures above here should be similar. And then from the Curie depth point to the MOHO, in the magnetic model, we don't have anything, but in the density we invert here still, and that it doesn't give you a completely different signal. It's quite good here that the gravity only behaves with the upper part. So yeah. I think it's quite cool. Yeah.
Different model outputs, you got a slide up there that shows the comparison with the lake to next. Yeah, there. How do you reconcile those differences with inversion parameters and tuning being so specific and sometimes minute? When those vast differences from?
Yes. So there are different approaches to the different heat flow models. So mine down here is based on the Curie depth, which we discussed before. So you find the bottom of the magnetic layer, and then you forward calculate, because you assume you have found the 580 degrees Celsius isotherm. You assume nothing particular major happens in the crust, and then you just put global average values for heat production and thermal conductivity, and then you can forward calculate to the top of, to the bedrock topography. And this approach is used by Martos and myself here. Those two are seismology studies. Arnett et al. Is quite old already and didn't have a lot of seismometers anyways. And that's purely based on receiver functions. So they had a few receiver functions, calculated the depth of the crust, and from that they forward calculate quite similar. Just if you know the transition zone. Yeah. Shen used tomography and in a quite interesting way, but it's inferred as well. So they have a continent-wide tomography model of Antarctica with quite a few stations. I'm actually not sure how that really works, but not as a seismologist. And they looked at the different the different propagation speeds of the waves. Then they looked at America, because in America we have they have a really good seismic network, US array, and good heat flow models. So they linked the American tomography model to heat flow models in America. And that same relationship between travel speed and heat flow, basically, they put back to the Antarctic tomography model and just applied that relationship. And that's how they came up with that model. Inherently has the problem that any tectonic process that happens in Antarctica but doesn't happen in America, they cannot explain that. And then we have basically two machine learning applications, and they put a lot of different data sets in there, basically distance to volcanoes, distance to the ridge, gravity, magnetics, topography, and some other stuff. I just have like a machine train the data. Marine and Jörg Ebbing train the machine learning application in Australia and applied it then to Antarctica. And I think STAR is basically all Antarctic data sets, different ratings that spits out a heat flow map, more or less. So they are all sensitive to different things. So the size model, the Anad Al is very sensitive to the MOHO depth. Shen is lithospheric scale model, sensitive to things that happens in America. If they happen in Antarctica as well, then good fit. And Marcus, my model, is sensitive to the Cree depth, which is has high uncertainties as well. So that's where you have different approaches. And I think the big difference in Stahl and Lösing is they use the global heat flow model, and Stahl, the heat flow model, the heat flow catalog has different quality checks next to the heat flow model from A, B, C. And I think Lösing used all of them, and Stahl only used the really good heat flow models. And that already infers, like, steers the machine learning to different solutions. So yeah, I'm for continent-wide heat flow models, they agree quite well. I think the Shen and Stahl look quite good, because but for local studies, I think we really need to tackle the unknown geology. But how to do that is, yeah.
Mentioned that there's a need for this constraining glacier models. I do glacier modeling, so that's very interesting to me. Do you have a model in mind that already has this capacity and needs better data to inform it, or so I haven't seen the capacity in models? Or you've already seen that and kind of better inform that, or prove that it's a necessary parameter in the first place.
Yes, there's a study by Felicita McCordy. I'm probably getting the surname wrong, but she run icesheet models and showed that heat flow is quite important, and what like on which resolution the heat flow model is. That's the only study I am aware of. 2021, I think. Spoke to quite a few ice sheet modelers in Edinburgh, and it turned out that they either still use MATOS or just one heat flow value for the whole model anyway, and don't really care that much. I think ice sheet models have the heat flow problem, but also like internal frictions anyway. So they have two unknown parameters where they can put their residuals in. I'm not sure if they care too much, but there's a geothermal heat flow community that definitely cares, that tries to address those things. But yeah, and again, I couldn't give recommendation which is the best model you should use. I would recommend not using MATOS really, because she has absurd high heat flow values in West Antarctica, up to above 280, which I think are unprecedented and not found anywhere else, and might be not right, but yeah, I mean, yeah, if I would try to find local solutions first, and then if that fails, I think Shen, Lösing, and Stahl are the best models to go with, because there's also a dipole, a magnetic dipole equivalent source approach from Fox-Mole, but that uses really old satellite data, which is probably not up to date. It's more a legacy data set, and et al. It's also quite outdated. So yeah,
The same approach could be applied to more recent satellite data.
yeah, I guess so.